Hello friends, in this video we are going to discuss about binary numbers and corresponding applications in DevOps. As part of this video we are going to discuss about what are binary numbers, what are hexadecimal numbers, and the applications of using these binary numbers and corresponding hexadecimal numbers. Basically, in computers the information is represented in terms of bits, which are nothing but zeros and ones. Computers can only understand the combinations of zeros and ones. So we need to understand how these combinations of zeros and ones will be used by computers. Not just the computers, these binary numbers, which are nothing but zeros and ones, are used in DevOps. So as part of the applications, we are going to see how various memory and disk sizes will be represented by the combinations of zeros and ones. We are also going to see how to represent the permissions of files and directories in Linux operating system. And we use binary numbers in various use cases in cloud, like subnetting, the representation of CADR, the IP addresses and MAC addresses of network interfaces, and so on. So in this video, we are going to see all these applications, how we are going to achieve by using different combinations of binary numbers. So let us start. Before discussing about binary numbers, let us go through a decimal system. We know that in decimal system, we use the combinations of numbers from 0 to 9. So we can use any of the combinations of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The total number of these digits is 10. So any number we represent in decimal system will have base 10. For example, if we take 1, 2, 3, the base is 10. So here this 1, 2, 3 is formed by 3 plus 2 into 10 plus 1 into 100. So in this number 1, 2, 3, each digit will have corresponding place value. So for example 3 here, units position will have a place value of 10 power 0. That means 3 into 10 power 0, which is nothing but 3. Similarly for 2, the place value is 2 into 10 power 1. For 1 it is 1 into 10 square, which is nothing but 1 into 100. As we go on from right to left, the place value of the number will increase. Similarly, if we take 275, this number is formed by 5 into 10 power 0, which is nothing but 1, plus 7 into 10 power 1 plus 2 into 10 square. So which is nothing but 200, and this is 70 and this is 5. So 5 plus 70 plus 200 is 275. So this way in decimal system any number will be formed by using the combinations of any of these numbers from 0 to 9. And also we have seen what is the place value of each of the numbers in the corresponding number. So now let us discuss about the binary system. The binary system uses the combinations of zeros and ones. So here we have only two digits, which are nothing but 0 and 1. So all the numbers or other information like characters, special characters, everything will be represented by using the combinations of zeros and ones. So let us start with single digit numbers. So if you want to form single digit number by using 0 and 1, either we can have a 0 or 1. That means we can have maximum 2 single digit numbers by using 0 and 1. So if we want to form 2 digit numbers, so this digit can be filled by 0 and this is also can be filled by 0. So this can be filled by 0 and this can be filled by 1. Similarly, we can form 1 0 and 1 1. So we can have maximum of 4 2-digit numbers by using zeros and ones. Similarly, for 3 digits, we can have 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. So here we can have 8 combinations of zeros and ones. That means total of 8 3-digit numbers can be formed by using combinations of zeros and ones. Similarly, 4 digits, it will be 2 power 4, which is 16. Similarly, for n digit combinations, we can have total of 2 power n. So by using these different combinations, we can represent the decimal numbers. That means the decimal numbers can be converted to binary numbers. This 0 0 means 0, this will be 1, this will be 2, and this will be 3. Similarly, for 3 digits, this will be 0, 1, 2, 3, 4, 5, 6, 7. So how we know this is 3 and this is 5? We have already seen in decimal number system. For example, 1, 2, 3, this will be multiplied with 10 power 0 and this will be multiplied with 10 power 1 and this is multiplied by 10 square. So that means 1 into 10 square plus 2 into 10 power 1 and 3 into, so 1 into 10 square means 100, 2 into 10 power 1 means 20, so 3 into 10 power 0 means 3. That is 1, 2, 3. Same way in binary digits, if you have like 1, 0, 1, 1, since this 1 is in units place, it will be multiplied by 2 power 0. So this will be multiplied by 2 power 1 and this will be multiplied by 2 power 3. So in binary digits, we have the base is 2. That is why we are representing each place value by the power of 2. So 1011 means 1 into 2 power 3 plus 0 into 2 square, which is 0, plus 1 into 2 power 1 plus 1 into 2 power 0. So that means 8, 2 and 1. 8 plus 2 plus 1, which is nothing but 11. Similarly, if we take 1, 1, 1, this is 1 into 2 power 0, this is 1 into 2 power 1 and this is 1 into 2 square. So if we add all these, which is 1, 2 and 4. So by adding these 3, we are getting 7. So 111 means 7. Now we have seen the conversion of binary to decimal. Let us see the conversion of decimal to binary. To convert a decimal number to binary, we have to divide that number by 2 and we have to note down the remainder. We have to continue this division until we get the quotient as 0. So let us take a number 31. Now I am dividing by 2. So the quotient is 15 and the remainder is 1. So now we have to divide 15 by 2. The quotient is 7 and the remainder is 1. Again I am dividing by 2. 3, 1, 1, 1, 0, 1. So now the quotient is 0. That means we can stop this process. So now we have to take all the remainders from last to first, which is 1, 1, 1, 1, 1. So this is in binary form. So let us take another number 60. So let us divide by 2. Quotient is 30 and remainder is 0. 15, 0. Quotient is 7. Remainder is 1. 1, 1. So now the quotient is 0. That means we can stop this process and we have to note down all the remainders from last to first, which is in base 2. That means the decimal number 60 is equivalent to the binary form 111100. So base 2 means it's in binary form. So we have seen the process of converting a decimal number to binary as well as binary to decimal. Next, let us move to hexadecimal numbers. Now let us understand hexadecimal system. We have already seen the binary to decimal conversion and decimal to binary conversion. Since the binary numbers contain large number of zeros and ones, it's very difficult for humans to read it as well as convert every time to decimal number. So there is another convenient way to easily understand the binary numbers by using hexadecimal system. In hexadecimal system, we group every 4 binary digits by a single symbol. For example, if we have a binary number like this, then we can group by dividing each of the 4 bits as a group. So this is one group and this is another group. So each group will be represented by a symbol. For example, this is 9 and this is 8. So this is in hexadecimal. So 1001001 in binary is equivalent to 89 in hexadecimal system. So this hexadecimal system uses 16 symbols to represent the information up to 9, then A, B, C, D, E and F. So these are the 16 symbols hexadecimal system will use to represent the binary numbers. So let us see how we can get those numbers. 0000 equivalent to 0, 0001 equivalent to 1, 0010 2, 0011 3, 0100 4, 5, 6 and this is 7 and then 100 is 8, 1001 is 9, 1010 this is A. So 10 is equivalent to A in hexadecimal. Similarly 1011 which is 11 in decimal and that is equivalent to B. 1100 is C, 1101 is D 1110 is E, and finally 1111 is F. So in hexadecimal we have these 16 symbols which represent the actual information. Though computers do not use this hexadecimal system directly, it is convenient for us to convert from binary to hexa and hexadecimal to binary. So let us take another example. For example, if we have this 12-digit binary number, then we can convert to hexadecimal by using the same process. So we have to divide each of the 4 bits as a group. So this is one group, and this is equivalent to B, and this is equivalent to 9, and this is 1, and this is D. So that means D19B in hexadecimal. So this binary is equivalent to D19B in hexadecimal. We can also convert this hexadecimal to binary by representing each of this element to 4 bits. So we can convert B to 1011, and 9 to 1001, and 1 to 0001, and D to 1101. So it is easy for us to convert from hexa to binary as well as from binary to hexa. So that is why we can use this hexadecimal system in various use cases for representing IPv6 addresses and also the MAC addresses of network interfaces and so on. So this is about hexadecimal system. Now we understand the binary system as well as hexadecimal system. Let us see some of the use cases as we discussed earlier. Now let us go through one of the applications of binary numbers, which is the representation of the sizes of memory and disk in the computer. In cloud computing, when we work with multiple clouds like AWS, Azure, Google Cloud, and Oracle Cloud, and so on, we create multiple virtual machines. While creating those machines, we allocate memory and disk to those machines. The size of the memory as well as disk are represented in terms of binary numbers. That means in powers of 2. For example, if we take 1, the place value is 2 power 0. That means 1 into 2 power 0, which is 1 in decimal. So this is binary and this is decimal. If we take 1 0, so here the place value is 0. That means 2 power 0 and 2 power 1. So this is 1 into 2 power 1 plus 0 into 2 power 0, which is 0, which is nothing but 2 power 1, and this is 2. Similarly, 100, this is 1 into 2 square plus remaining all will be add up to 0. That means 2 square, and this is 4. Similarly, 1 triple zeros, 2 cube, and this is 8. 1 4 zeros, 2 power 4, and this is 16. Similarly, if you have like 10 zeros, that is equivalent to 2 power 10, which is nothing but 1024. If you have 20 zeros, then that is 2 power 20, which is equivalent to, similarly if you have 30, that is 2 power 30. So this is equivalent to this number. So why we are representing here like this? This is because the memory and disk sizes are represented in powers of 2. For example, we have 1 kilobytes, which is nothing but 1k into 8 bits. So here 1k means 1024. So this is also called 1 KIB, means kibibyte. Similarly, this is equal to 1 MIB, which is nothing but 1 mebibyte, and this is equal to 1 GIB, which is nothing but 1 GB byte. So here the disk sizes or memory sizes will be represented in terms of kibibytes, mebibytes, and GB bytes, and so on, which are nothing but the actual binary number values that are equivalent to powers of 2. So this is how computers understand the sizes. But as humans or manufacturers, we represent the sizes of disk or memory in terms of decimals. For example, manufacturers will treat this as 1000, which is nothing but 10 cube, and they will specify it as 1 kilobyte. So 1 kilobyte is approximately equal to 1 kibibyte. 1 kibibyte means 2 power 10. So 2 power 10 is almost equivalent to 10 cube. Similarly, manufacturers will approximate this as 10 power 6. So they call it as 1 megabyte. So 1 megabyte or approximately equal to 1 mebibyte, which is nothing but 2 power 20 is equivalent to 10 power 6. Similarly, they approximate this as 10 power 9, which we call as 1 GB. So 1 GB approximately equivalent to 1 GIB. So 1 GIB in computers is approximated as 1 GB by manufacturers. That is why when we allocate RAM or disk sizes by the manufacturers to the machines, the actual values will be lesser than these sizes. So let me explain that. Here let's take an example. For example, we have created a virtual machine and we have attached 4 GB RAM to that machine. When we say 4 GB, that means 4 GB in decimal. So which is nothing but 4 into 10 power 9 bytes. But in our computers, the OS will represent the memories in terms of GIBs. How much this 10 power 9 bytes will be represented in terms of GIB. So we know that 1 GIB is equal to 2 power 30. So 2 power 30 is equal to 1 GIB. So 10 power 9 bytes is equivalent to how much GIB? So this is equivalent to 10 power 9 by 2 power 30. This is for 1 GB is equivalent to 10 power 9 by 2 power 30 GIB. Then 4 GB is equivalent to 4 into 10 power 9 by 2 power 30. So if we calculate that, we will get around 3.725 GIB. So 4 GB RAM which is allocated for the virtual machine is equivalent to 3.725 GIB. That means when we search for the RAM in the operating system by using Linux commands, then we will see the amount of memory in terms of 3.725 GIB. So let us check that in one of the Ubuntu operating systems. This is a Ubuntu operating system. So here 4 GB is allocated for this machine. So let me check the memory in terms of GIB. So here we can see the total memory is allocated as 3.7 GIB. So this is GIB, not GB. So actually 4 GB is allocated to the machine, but we can see 3.7 GIB because the memory is represented in terms of powers of 2, not in decimals. Here in this table we have summarized different sizes. 1 KIB, which is 2 power 10, is approximated as 1 KB by the manufacturer. Similarly, 1 MIB is approximate to 1 MB, 1 GIB is approximate to 1 GB, 1 TIB is approximated to 1 TB, and so on. So this is how the memories and disk sizes will be represented in terms of binaries or powers of 2. Now let us move to another application of binary numbers. Now let us explain another use case, file and directory permissions in Linux. So here we can use the combinations of bits to assign the permissions on the files and directories in Linux. In Linux, we have three types of people. One is user or owner, and then we have groups for which the users belong, and finally we have others. So these others are not belonging to any of the groups. These user or owner or groups or others will have permissions read, write, and execute. So if we have to provide permissions on the files or directories, we need to provide corresponding read, write, and execute permissions to any of these people. For example, we have a file named test.txt. So if we want to provide the read permissions on this file to the owner, then we have to provide corresponding read permission. So if we want to provide the read permission to groups, then we have to provide that permission. Similarly, we can provide read permission to others. Similarly, we can provide the write as well as execute permissions. That means we need to provide the combination of permissions on a particular file or directory so that corresponding permissions will be assigned to users, groups, or others. So here, since we have read, write, execute RWX, this read, write, and execute permissions will be assigned by using the combinations of zeros and ones. So if you want to provide read permission, we need to assign 1 to read. If you want to provide write permission, we need to assign 1 to write. Similarly, if you want to provide execute permission, we need to assign 1. So if you don't want to provide read permission, we need to assign 0. If you don't want to provide write permission, we need to assign 0. And similar to that, for execute permission also, if you don't want to provide, we have to assign 0. Since we are using binary numbers here, zeros and ones, we have total combinations of 8 permissions. So for example, this is read, write, x. We have 0, 0, 0. That means we do not provide any permission. That is equal to 0. And if you want to provide only execute permission, 0, 0, 1, which is 1 here. 0, 1, 0. That means we are providing only the write permission. 0, 1, 1. That means we are providing write and execute permission, but not read permission, which is 3 here. And if you want to provide only read permission, and we are not providing other permissions, then this is 4. So the next permissions will be 101, 5, 110, 6, 111, 7. So 111 means we are providing all read, write, and execute permissions. So these are 8 combinations we can assign for a particular file or directory. So these combinations can be assigned to either user or groups and others as well. So to assign the permissions on the files and directories, we will use different combinations of zeros and ones so that corresponding permissions will be assigned either to user, groups and others. So let us see some of the examples now. So now let us see some of the examples here. So this is the first example. Here we have a directory named build and we have to provide the required permissions on this directory. So what needs to be done for this? So in this case, the user or owner needs to have full permission, the group needs to have read and execute permissions, and others need to have no permissions on this directory. So in Linux, for providing permissions, we use a command called chmod. So now we need to provide required permissions as per the specifications here. So let us write user, group and others. So we have read, write, execute. So the user needs to have full permission. That means we need to provide 1, 1, 1 on read, write as well as execute. The group needs to have the read and execute permission. That means R should be 1 and X should be 1. Since we do not need to provide write permission, we have to mention 0 here. And others need to have no permission. That means we should not provide any permission. So this should be 0, this should be 0 and this should be 0 as well. So the user permission should be 7, group permission should be 5 and other permission should be 0. So we need to provide here 7, 5, 0 on the directory name build. So this command needs to be executed based on these given specifications. So let us go to another example. We have a script named deploy.sh. We have to provide permissions based on the below specifications on this file. So here the user or owner needs to have full permission. The group needs to have read and execute permissions. Other needs to have only read permission. So the user needs to have full permission. That means 1, 1, 1. Group needs to have read and execute permission. That means read 1, execute 1 and write is 0. And other needs to have only read permission. That means read should be 1, write should be 0, execute should be 0. So this is 7 and this is 5 and this is 4. So we need to provide chmod 754 on the file deploy.sh. Let us take another example. We have a file called secrets.txt and we have to provide permissions as mentioned below. So user or owner needs to have read and write permission. That means this should be 1, this should be 1 and this should be 0. Group needs to have read permission. So this should be 1, 0, 0 and other needs to have no permission. That means 0, 0, 0. So this is 6, 4 and 0. So we need to provide chmod 640 secrets.txt file. So this command needs to be executed here. So this way, based on our requirement, we need to provide the required permissions on the files and directories by using different combinations of zeros and ones. One more thing we have to note here is that in Linux, there is a concept called umask. So this specifies what are the default permissions on the files and directories in Linux. For example, if you create a directory or a file, so that will have default permissions. So based on the umask value for directories, the default permissions will be obtained by subtracting the umask value from 777. Similarly, for files, the umask value should be subtracted from 666. For example, if the umask value is 22. For example, if the umask value is 022, then if you create a directory that will have default permissions 777 minus 022, which is 755. So that means read, write, execute, read dash execute, read dash execute. Here dash indicates 0. For files it is 666 minus 022, which is 644. That means read, write dash, read dash dash and read dash dash. So this is the default permission of a file when the umask value is 022. So let us log into one Ubuntu machine and let us go through some of the examples. So let's start the demo. This is a Ubuntu machine. Let us try to create some files and directories and let's check the permissions. Before that, we have already seen the default permissions for the files and directories will be obtained based on the value of umask. So let us see the default value of umask here. So this is 0022. For directories, if we create, the default permissions would be obtained by subtracting from 777. So if we do that, that means 777 minus 022, that means 755. So the default permissions for the directory should be 755. So let me try to create a directory here. So I have created a demo directory here, and the default permissions are, so here the D indicates it's a directory, RWX means 7, R-X means 101 which is 5, and this R-X means it is also 5. That means the default permissions are 777 minus 022 which is 755. So if we want to change these default permissions, the umask value should be changed accordingly. So now let us go to the demo directory. So here let's try to create an example file. So I have created a test file here. Let me add some example content. Let's see the default permissions of this file. So here we can see the default permissions of a file are obtained by subtracting this umask value from 666. So this is 6 and this is 4 and this is 4. So that means 666 minus 022 is equal to 644. So which is the default permission for a file based on the umask value. So these are the default permissions. So let us try to change the permissions of this file now. So here the user or owner has the read-write permissions on the file, and the group has only read permissions. Others have only read permission. So if you want to change the permissions of this file, for example, if you want to provide the write permissions for the group, that means this needs to be changed. For changing the permissions, we can use chmod command. So we are not changing the permissions for owner. Let us keep the existing permissions. That means 6. Since we are assigning the write permissions here, that means we have to make this dash as W. So RW dash, that means 110. So this also should be 6. And we can keep the default permissions for others. That means 100 which is 4. Now we can see the group is also having the write permission. For example, if we have a script and if you want to give the read and execute permissions to others by keeping the permissions for user and group unchanged. So that means we have to provide execute permissions here. That should be R-X 101 which is 5. So let us provide that permission. For users it is already 6. For group it is 6. Since this is R-X, that means 101 which is 5. So let's verify the permission. Here we can see the execute permissions is provided to others for this file. Let's take another example. For example, if we need to provide all permissions for the user or owner and provide read and execute permissions for the group and others. That means here we are not giving the write permission. So in this case, since we need to provide all permissions, that means RWX which is 111. So that should be 7 for the user. Read and execute permission, that means R, we are not giving write permission, that is dash, and execute means X. So 101, so it should be 5, and also for others it should be 5. So let's copy this. Now let's verify the file permissions. So here we can see the user has all the permissions, the group as well as others having read and execute permissions. Similarly, we can provide the permissions for the directory as well. So currently it is having 755 permissions. So if we want to change the permissions for this directory, again we need to change the combinations of this RWX by assigning corresponding combinations of 1 and 0. So for example, if we do not want to allow the read and execute permissions for this directory to others, so we need to remove those permissions. So in that case, so it is 7, 5 and it should be dash dash dash, that means 0 0 0 which is 0. So for that we need to provide 7 5 0. So here we can see dash dash dash, which means no permissions for others. For example, if we want to provide the write permissions for group here, so then we need to make it RWX, which means 111. That means we need to provide 7 to the group. For owner it is already 7. For group it should be 7 now. And for others it is already 0. So let us check the permissions. Here we can see the group is having all permissions now. So in this way we can change the permissions for the files as well as directories by using the combinations of ones and zeros. So in this video we have gone through what are binary numbers, and what are hexadecimal numbers, and the applications of these binary numbers, like the representation of the memory and disk sizes in the computers, and the permissions of files and directories in Linux operating system. I also wanted to explain subnetting, CIDR, IP addresses and MAC addresses and so on, but the size of this video is already more, so I would explain that in the next video. I hope the content is useful to you. If you like the content, please like, share and subscribe. Thanks a lot for watching.